Hello, my name is Lorenzo Giraudi and I work for Ideas in Motion. I will be presenting you the platform that we designed for the Trust Vehicle project. One of the objectives of Trust Vehicle is about controllers and sensor fusion systems that are a fundamental part of ADAS application. Ideas in Motion focused on the hardware side of this to design a platform able to safely run this software. First of all, you need a high-performance system on chip capable of processing large amounts of data coming from sensors. But since it will perform safety-critical tasks, we want it not to send erroneous and potentially hazardous data to the output, even in case of failure. A safety certifiable processor has to monitor its health status and eventually act on it, for instance, by resetting it. We started from this idea and developed the Sensor Data Fusion platform, a system with two different processors, an i.MX8 Quad-Max from NXP and an AURIX TC297 from Infineon. The first one is a powerful system-on-chip with 6 ARM cores running at more than 1 GHz, an integrated GPU, and external dynamic memory. The second one is an automotive microcontroller that is ASIL-D certifiable with lockstep cores and several safety features. We chose to split the system and put the i.MX8 on a small system-on-module, following the SMARC standard that defines the form factor in the interfaces, so that there is interoperability with other system-on-modules. The AURIX and all the other peripherals are on the big board called Carrier. Here is a quick look to the system. You can see that it has a diverse set of interfaces, like CAN and LIN, alongside with interfaces more useful for testing and debugging, like SD card slot and USB. Mini PC Expert slots give the possibility to add functionalities, like, for instance, LTE connection or GPS. Moreover, the board has two 100 base T1 Ethernet, also known as Automotive Ethernet, and also the two higher bandwidth Gigabit Ethernet. And in order to showcase the potential of this platform, we took part in Tofaş demonstration. We deployed Linux on the i.MX8, and on top of that lays the ROS framework. There are two ROS nodes. The first one parses the data coming from the LiDAR. And the second one shows the samples on an HDMI display connected to the SDF. Moreover, the data is forwarded to Tofaş PC for further elaboration. In the meanwhile, the AURIX monitors the health of the other processor. So in order to show its correct running status, the i.MX8 has to send an SPI message every 20 milliseconds, and it has to be within a valid window. Too early or too late, and the AURIX will consider it as an error. This is to ensure that the kernel is not stuck. After 5 errors, the AURIX resets the i.MX8. Every time a correct message is received, the error counter is decremented. Moreover, the content of the message is an upcounting value that is getting incremented on both processors after every transaction. The AURIX checks that the correct value has been set. In this way, we ensure that the i.MX8 is not sending always the same message. Finally, we connect a toggle switch to the i.MX8 so that when you activate it, the kernel gets a fault and thus stops sending messages. On the left, you can see the SDF in Tofaş vehicle. Since we could not go to Tofaş in person, we replicated the same setup in our lab and performed there the measurements. We connected two PC to the board, one of which will mimic the LiDAR. We used a ROSBAG that is a pre-recorded log of data that you can play like a video. It contains all the samples from the sensor over a period of time. The other PC will receive the data and show it with a visualizer called RViz. The purpose is to show that the SDF is forwarding the LiDAR samples and it takes place of the Tofaş PC. Here is a diagram of the architecture. On the left is the PC playing the Rosbeg, mimicking the LiDAR. In the middle there is the SDF and the HDMI display connected to it. On the right, the PC with the visualizer, whose purpose is to show that the SDF is forwarding the data. Now I'll be starting the play of the Rosbeg. And you can see that the data is updated on both displays. Now I'm showing you a video taken inside the Tofaş vehicle. And you can see the silhouettes of the parked cars along the narrow street scenario of the Tofaş demonstration. The red box on the left is the position of the Eagle vehicle, and this is a top view of the obstacles. And here finally you can see the pedestrian crossing the street. Now I toggle the switch that trigger a fault in the kernel, and you can see that after the kernel fault the SPI message stops and the AVRIX takes 162 milliseconds to detect it and then reset the AutoMakeSite by driving a low pulse on the reset signal. All the measurements that we took were around 162 milliseconds, all up in the range of 1 millisecond plus or minus 1 millisecond. And now you can see that the graphical interface is starting again, and it also resumes forwarding the data to the other PC. So, in the end, what we got? We have designed the hardware platform from scratch and tested all the peripherals and safety features to see that they work correctly. The demonstration itself, we deployed Linux and ROS, and they both correctly worked. We managed to bridge the Ethernet ports to the AutoMakeSite, thus creating a network between the LiDAR, the SDF, and the Tofaş PC. We also got a rough but working graphical interface. On the safety side, we demonstrated the basic of a fail-safe behavior, and the current monitoring protocol is a good base for more elaborated ones that we will study in the future. In conclusion, we can say that design platform is suitable for future sensor fusion prototypes. Thank you very much for your attention, and if you have any question, please leave them in the Q&A section and I will answer to you later.